Hello everyone and welcome to my MSc Defense. My name is Abdurrahman Karim and the thesis title is Synthetic Data Generation for Training and Evaluation of Deep Learning Based Computer Vision Models. The thesis supervisor is Dr. Ufuk Chalijan. Before starting, we would like to thank all the jury members for their valuable time and for being here with us. Now, in this few minutes, we will try to cover the following points. So first of all, our motivation behind the thesis research. Second, the available synthetic data generation approaches and why did we select the specific approach that we employed in our NOVA framework. Then we will discuss the NOVA framework in more details, and since our contribution and our work is dedicated for visual object tracking, we will discuss some of the available and famous visual object tracking datasets. Then after that, we will show how we can use our generated synthetic data for evaluation and training purposes. That will constitute the first part of our research. Now the second part, which is based on some facts that we found in the first part, is much more dedicated toward the adverse weather condition, right? Toward the adverse weather condition. So first of all, we will show the main attributes that were implemented toward improving the adverse weather condition simulation. Then after that, we will show two data sets that we provide with the second work, PTAU 172 real and the PTAU 217 synthetic data set. Then after that, we will show how the state-of-the-art visual object tracking algorithms perform poorly under adverse weather condition and how can we use our synthetic data to improve their performance. Finally, we will conclude our presentation. Well, we can see nowadays that learning-based methods are showing great progress in the field of computer vision. However, for these methods, learning-based methods, in order to perform well, they require a lot of labeled data. Now, the issue is that collecting and annotating data is not only expensive, but error-prone and subject to privacy issues. Now, because of these mentioned reasons, now we started to see a bottleneck. Now, this bottleneck in terms of the availability of labeled and diverse data for training or for evaluation. And we can see that one of the best solutions for this problem is using synthetic data. Now clearly we can see why do we need synthetic data. For synthetic data, when we look to the literature, we can see that we have many approaches to generate diverse data. However, let me describe here the mainstreams for data generation. So the first one is adapting a video game. The second is adapting a graphics engine. The third is using a simulator framework, while the fourth one is using some open source animation movies. However, the best approach in terms of diversity, scalability, and also its generalizability to different computer vision tasks is using a graphics engine and applying procedural generation techniques as we have done in our NOVA rendering. Now, in order to generate synthetic data, we built a novel framework. We call it NOVA. So the main characteristics of this novel rendering engine, first of all, it's built using the Unity graphics engine, and also it is a good choice for research groups with limited budget, so it can run on current generation hardware. Another important point that for computer vision researchers, they can use it very straightforward, so we don't require from them any computer graphics background. So generating a large data set with accurate annotation is really straightforward. So they just need to specify the attributes of the dataset that they would like to have, and they will have the dataset generated for them on the fly. Now, one key characteristic of NOVA is the ability to populate scenes with photorealistic, diverse humans. theoretically we can generate unlimited number of humans, where we can diversify the attributes, the humans attributes like the age, weight, gender, skin color, and many other attributes. Now, in addition to the diversity of the humans, we have another layers of diversity or another dimensions of diversity in terms of the scenes, the weather conditions, the times of the days that we have. Now, the diversity is a very important factor if we are talking about using our synthetic data for training or using our synthetic data even for testing. Now, our rendering engine was built to be a general purpose tool. So here we support many different computer vision tasks like optical flow estimation, like surface normal estimation, like depth estimation, instance segmentation, semantic segmentation. In addition to different tasks related to humans, like we can find the bounding box for the pedestrians, we can provide the body segmentation and also the body pose information, plus rich textual information describing the scene, describing the weather condition, the time of the day, the gender of the pedestrian, and many other features. Now, after having an idea about the diversity of the synthetic data that we were able to generate, now let's have a look at a comparison in terms of the photorealism between our data and the available real data for the visual object tracking. So here we consider different visual object tracking datasets like NOSPRO, Temple Color 128, UAV 123, OTB 100, and VOT and MOT. These datasets, they are very famous, and you can see here for each row we consider one dataset and we show the first 3 frames from these real datasets, and the last 2 frames are examples generated using our Nova rendering engine. You can see from this figure that we were able to generate a photorealistic samples that are similar to the available visual object tracking datasets. Now we try to prove the usability of our synthetic data for testing purposes. So we generate a synthetic dataset called Virtual PTB1. It stands for Virtual Person Tracking Benchmark, and this dataset contains different challenging attributes like for example, adverse weather condition, like crowded scenes, like challenging camera setups, and like challenging illumination conditions. When we check the state-of-the-art trackers performance on this dataset, we can see that some certain attributes cause these trackers to perform poorly or to completely fail. So here you can see the heat map showing the precision of each tracker on each sequence of this data set. In more details, we can see that crowded scenes or nighttime or foggy weather conditions or high camera altitude present a clear challenge for some state-of-the-art tracking algorithms, right? Now, the second aspect of proving the usability of our data is using it for training purposes and showing that when we use our synthetic data, we can boost the performance of state-of-the-art tracking algorithms. Now, for that reason, we consider 2 state-of-the-art tracking algorithms, that is DIMP and CFNet. Now, for training, we consider 3 training scenarios. 1, we use our synthetic data only for training. The second one, we use real data only for training. And in the third scenario, we use a mixture of both synthetic and real data. Now, for training, we train on synthetic data. We train on our data from scratch, as done in E1, E2, and E3 experiments. Now, at the same time, we do fine-tuning on the baselines that are provided by the authors, as shown in E4, E5, E6. At the same time, we report the results of the baselines of these two trackers. As you can see from this plot, fine-tuning the baselines on a mixture of synthetic and real sequences improves the performance. At the same time, training on synthetic sequences alone achieve better results compared to training solely on real sequences. Now, what we have discussed so far constitute the first part of my master research. So here we prove the usability of our generated synthetic data for testing and for training purposes. However, as you can see, there is a clear gap in the available videos for adverse weather condition. Now, because of this, we dedicate our second part of research to fill this gap and to provide some useful data sets, whether for training or for testing purposes, for the visual object tracking under adverse weather condition, as we will see in this part. Now, when we study the available visual object tracking datasets, whether they are real or synthetic, we can see clearly that the adverse weather conditions are absent. So, in order to solve this problem, we provide two datasets. Real dataset TAU172 real, which can be used for testing purposes, and TAU217 synth, which can be used for synthetic, which can be used for training purposes. So you can see the two datasets that we provided spans different adverse weather conditions: rainy, snowy, and foggy weather condition. Now let's discuss the two datasets in more details. So first of all, let's consider TAU172 real. So it stands for person tracking under adverse weather condition, and here you can see that we provided 172 172 videos. So this data set was collected from YouTube and was annotated by us. So here you can see samples from these three adverse weather conditions, where each weather condition is depicted in one row. So here you note the diversity of these. You note here the diversity of scenes, the diversity of illumination, diversity of crowdedness levels, and camera setups for each weather condition. Now, at the same time, for the synthetic data set that we provided, I mean TAU217 synth, we provided here 217 synthetic sequences generated by the extended version of Nova rendering engine. You can see here the diversity and the realism, the photorealism of the generated synthetic sequences. So for each row we have a different weather condition, as you can see. Now, at the same time, we know that if we would like to use our synthetic data for training purposes and to achieve a good results, we have to be careful about the domain gap problem and to try to minimize or to try to mitigate this problem. So here we provide a comparison, a visual comparison among the real and synthetic data set and the synthetic data set, and you can see they are really close to each other in terms of the appearance. Now, when we check the performance of the state-of-the-art tracking algorithm on this real adverse weather condition dataset that we collected, you can see that these adverse weather conditions present a certain challenge on these datasets. And here you see the results for the precision or the success score that they are quite low for some state-of-the-art tracking algorithms. Now, in order to improve the performance of these state-of-the-art trackers under adverse weather condition, we train using our synthetic sequences that we generated using our Nova rendering engine. So you can see the overall performance here in this figure. So the baseline is shown in blue, and training from scratch on our synthetic data is shown in green, and here in yellow, fine-tuning on our synthetic data is shown here for 4 different trackers. They are Atom, DIMP, PRDIMP, and KYS. So as you can see, fine-tuning or training on our synthetic data can improve the tracker performance under adverse weather condition. At the same time, we study how we improve the performance of these trackers for specific under a specific weather condition, like for snow and rain and fog, and we can see we were able to improve these trackers' performance under each specific adverse weather condition. Now, in addition to the quantitative results that we have shown earlier, we show here some qualitative results. As you can see, the training on our synthetic data clearly improve the baselines. Now, since we provided the full occlusion, the scale change, the background clutter, and the sudden camera motion and notation for the videos, for the real videos that we have collected, we study the performance of these trackers for these specific attributes, and we show that we were able to boost the performance of these trackers for each specific attribute, as you can see. At the same time, we show here that background clutter causes the trackers to perform poorly, as you can see in this example. Now, let's conclude what we have presented so far. So first of all, we presented a novel procedural content generation engine called Nova, and this engine is capable of generating unlimited number of synthetic sequences that is diverse and photorealistic. In order to prove the usability of these synthetic data, we generated 2 synthetic data sets specifically designed for person tracking. Now we show that the existing trackers perform poorly in highly crowded scenes or in scenes captured at night and in foggy weather conditions. The generated synthetic sequences present a good proxy of the real sequences and can be used for testing and training purposes. Now, in the second part of the research, a novel real data set called PTAU 172 Real for visual object tracking under adverse weather condition was presented and annotated by us. Now, the poor performance of the state-of-the-art trackers under adverse weather condition under the real data set that we collected was shown. And using our Nova rendering engine, we generated a novel synthetic dataset called PTAU 217 Synth, made up of synthetic sequences under adverse weather condition. Now, using our synthetic data for training, we were able to show that we can boost the tracker's performance under these adverse weather conditions. And finally, I would like to thank you all for listening.